Well, good morning, the two of you. Nice to have you on board. Get started here. I wanted to see the lesson, as you can see, is lesson 4.2, Rolle's theorem and the mean value theorem. But the first thing we'd like to do is see if you have any questions on 4.1. So we were supposed to what? Find critical numbers and then find max and min. Morning, Richard. So questions on lesson 4.1. Any you would like to go through or look at? 43, okay? Oh, do I? Yeah, here's 43. Okay. So the function is e to the x multiplied by the sine of x, and the interval we're supposed to take a look at is from 0 to pi. Good morning, Jen. So we're looking at number 43 question on lesson 4.1 at the moment. All right. So the derivative of e to the x times, well, you use the product rule, the first times the derivative of the second, which is the cosine of x, plus the second times the derivative of the first, e to the x. Okay, we've got e to the x in both terms, so we can factor it out, which I did in this line right here. Factored out the e to the x. All right, now e to the x is this expression. You know, e is 2.7-ish, and no matter what you do with x as the exponent, you will never get that to be 0. So basically, that here we have two things being multiplied that equals 0, and this one can never be 0. Therefore, this is the culprit, cosine plus sine. When is that 0? So I set that equal to 0, and then I just subtracted the cosine of x from both sides. And now we had to ask ourselves a question: when are the sine and the cosine the same value with the opposite signs? Well, they're the same value at 45 degrees, right? Cosine of 45 is 1 over the square root of 2. And the sine of 45 is 1 over the square root of 2. Now the question is, when are they the same number but opposite signs? So now we got to think in quadrants. First quadrant are both positive, so that's not it. Second quadrant, the sine is positive and the cosine is, so that's possible, the second quadrant. And if you look up here, that's it. We don't have to look any further because we can only go up to 180 degrees. All right, so it's the second quadrant. What is a 45-degree angle in the second quadrant? Halfway between pi over 2 and 1 pi would be 3 pi over 4. So there's our critical value. X equals 3/4 pi. All right. Now add that to the beginning and the end of the interval. And now we've got the values that we need to check out. So go back to the original function. What is f of 0? E to the 0 is 1. The sine of 0 is 0. And 1 times 0 is 0. Okay? When you have 3 pi over 4 and plug that in, you get e to the 3 pi over 4 times the sine of 3 pi over 4, which is 1 over the square root of 2. Anyway, that one you're going to have to crank out decimal-wise. And that turns out to be 7.46. And then pi, e to the pi times the sine of pi. Sine of pi is 0. So basically we have 0, 7.46, and 0. What's the high? 7.46. What's the low? 0. End of problem. So that's number 43 from lesson 4.1. I think we did that one in class yesterday, but I'm happy to go through it again. Any other questions from lesson 4.1? 33, okay? Oh yeah, so 33 is that problem where, remember that bracket stands for the greatest integer? Okay, now you know what that looks like. That's the step function. It's just this horizontal short bars, right? Okay, I mean, hopefully, Richard, you can picture what that looks like. So, I mean, the thing is forever horizontal, but it changes. These steps change as you move along. So we're supposed to check this out between -2 and 2. I mean, as far as critical values, everything is horizontal, so there's really nothing to check out. We don't have to find when the first derivative is 0. So what is f at -2? What is the greatest integer of -2? It's -2. And what's the greatest integer on the other end of the thing? 2. All right. What's the min? What's the max? We're all done. You know, just to maybe make that a little bit more complete. Okay, we'll make a quick sketch here. So at 0, what's the greatest integer of 0? What's the greatest integer less than or equal to 0? 0. And then we've got 1/2. Here, let's just say this is 1. At 1/2, the greatest integer of 1/2 is 0. At 3/4, it's 0. So we've got all these points together. And as soon as we get to 1, it jumps up to 1. So this is an open dot. Then it jumps up above, and then it stays there until we get to 2. You know, and we have this step function developing that looks like this. Okay, so at f of 2, you can see the answer is 2. And if I would have gone to, so anyway, the different thing about this is, I mean, if you take the derivative of that thing, it's forever got a horizontal tangent. So it makes this problem of a different nature. There really are tons of critical numbers. So basically all we had to do is look at the endpoints, because in between the endpoints, it's basically staying level until it jumps. Any other questions on lesson 4.1?
Could we go over number 27?
Certainly. Yeah, so here's 27. 3x to the 2/3 power minus 2x. All right, and we've got the interval from -1 to 1. All right, so we need to find a derivative. So I use the power rule. 2/3 multiplied by 3 is 2. Reduce the power by 1 goes to x to the -1/3, and the second part's minus 2. Okay, now when is that? So that's the derivative. When is that derivative equal to 0? We can find out by setting it equal to 0, which I have done. And then we can get that 2 on the other side. And okay, so we look at this. 2 equals 2 over the cube root of x. And we see that x cannot be 0 because that would create an undefined derivative. So there's a critical point at 0. And when x is 1, this is going to work, right? I mean, I didn't go to the final step and cross multiply here, but it's the cube root of, the cube root of what cube root equals 1, and the cube root is 1. So we have two critical points. Some people might have forgotten that bottom one. All right, so now we take these 2 points along with our endpoints, and over here on the right, we find out what is the function at each of those. By the way, 1 is a repeat, it's a critical point, and it's an endpoint. So at -1, what's the cube root of -1? -1, and then -1 squared is 1, and 1 times 3 is 3. And then you have -2 times -1, which is +2, and 3 plus 2. So we wind up with a 5. At 1, the cube root of 1 is 1. 1 squared is 1. 1 times 3 is 3. And 3 minus 2 is 1. And then at 0, everything's 0. What's the max? 5. What's the min? 0. So that would be number 27. Thanks for the questions. Are there any other 4.1 questions you'd like to take a look at? Okay, well, let's get to the lesson then. Yeah, I guess let's just lesson, there are 2 theorems here we're going to take a look at. One's called Rolle's theorem, and the other one's called the mean value theorem. They're alike, and so they really fit together. So here's Rolle's theorem. Rolle's theorem, if you've got a continuous interval from, so in other words, from A to B, this thing is continuous, and it's differentiable everywhere from A to B. And if it starts at a point that's in equal height to the other, like you see here, we started at this height, we ended at this height in both cases, then there's got to be at least one point between these 2 endpoints where we have a horizontal tangent. So look at this picture here. So we start at this height, we end at the same height, it's continuous. Well, then it's got to reach a point sometime where it hits a slope of 0, a horizontal tangent, as the blue line indicates. That's Rolle's theorem. Now, this one, do you see, has a problem. It starts at the same height, ends at the same height. It's continuous, but what's not happening here? Let's see, I gotta get out of this mode. What's not happening here? Do you see that this one is not differentiable at every point, especially that point right there? So that one, so is there a place on this function on the right where there's a horizontal tangent line? You notice there is not. That's because it doesn't fit this part of Rolle's theorem. It's got to be differentiable at every point. Okay. So based on that, we can come to some conclusions and solve some problems. So here's the first one. We've got a function. I think you will all agree that it's continuous. You can see the picture of it here, the black graph. Okay. So Rolle's theorem ought to work here. It's at the same height on the 2 ends. In this case, they've got the two pieces of the same height are -1, 0, and 2, 0, the x-intercepts. And therefore, there's got to be a point between those two where we have this blue tangent line that is horizontal. So anyway, here's the equation, x squared minus 3x plus 2. And now we should be able to take, we certainly can take the derivative of x squared minus 3x plus 2. And what is it? 2x minus 3. Okay. When is that derivative, 2x minus 3, equal to 0? So we would just set it equal to 0, and real easily we can solve. Sorry, I'm having a little trouble writing on my screen here. This is just a 2. And then, so when x is 3/2, and sure enough, that's halfway between 1 and 2 right there. When x is between those two, sure enough, it does have a horizontal tangent point, horizontal tangent line at that point. Okay, so Rolle's theorem guarantees that if you've got 2 points of equal height and the function's continuous, it's got to have a horizontal tangent somewhere in between. And therefore, we ought to be able to find it. We got another one here. Yeah, here's another one. Here we have a little more complicated function. You can see it's a 4th power function. X to the 4th minus 2x squared. Find all values of c in the interval from -2 to such that the derivative is 0. Okay, well, at -2, when you plug it into the function, what do you get? -2 to the 4th is 16, and -2 squared, 4, so 16 minus 8 is 8. So the point is -2 comma 8, and that's this point here on the left. That's that one. And if you plug in a +2, you'll also get an 8. So you see we have 2 points of equal height. Therefore, somewhere in between those 2 points, between -2 and 2, there must be at least one place where it hits the tangent, where the tangent line will be 0. And in fact, you see on the picture, there actually are 3 this time. 3 places where it hits that. So step 1, find the derivative. Easy derivative, power rule, 4x cubed minus 4x. Okay, when is that equal to 0? So we set it equal to 0, and we can factor that. In fact, you can take a 4x out, and then what's left? X squared minus 1, which is a difference of 2 squares, and that can be factored. So you can see there are 3. When will 4x be 0? When x is 0. When will x minus 1 be 0? When x is 1. When will x plus 1 equal 0? So this says, hey, there are 3 places where there's a horizontal tangent. At x equals 0, at x equals 1, and at x equals -1. Okay, so remember, Rolle's theorem guarantees there's at least one. And in this case, we got a bonus. We actually have 3 of them. Okay, so does anybody have any questions on Rolle's theorem? Basically a guarantee that if it's continuous and if it's differentiable at every point between those endpoints, then you're guaranteed to have at least one place where you have a horizontal tangent. And we can easily find it by finding the derivative and solving that derivative. When is that derivative equal to 0, like we did here? And you will get at least one place. And sometimes you get more, like the problem we just did. Okay, it's time to move on to the second theorem, which is almost identical. called the mean value theorem. And this is basically Rolle's theorem tipped a little bit. What I mean by that is, do you remember when we looked at Rolle's theorem in the beginning? We saw that the 2 points that we started off with being, they're of equal height, horizontal from each other. Okay? The mean value theorem says, well, these 2 points, they're not of equal height, but you can see we have a slope there, and there's at least 1 point in between where the tangent line has the same slope as the beginning point. So it's basically the Rolle's theorem just tipped on an angle. That's all it amounts to. So this time, instead of us automatically looking for 0, we've got to figure out the slope of this bottom line here. And we all know how to do slope. Once again, I don't want to belittle. This has the same requirements. It's got to be continuous, and it's got to be differentiable everywhere on the interval. Okay. So here's our first example. Find a tangent. So find a tangent line so that it had, so the tangent line up there in blue on the top, left of the pink there. So that, yeah, let me go to something a little bit bigger here so you can see it more easily. Yeah, so this blue line on the top, find when, at what point for x will that tangent line be parallel to that original value of those 2 points? Well, they gave us the 2 points, or the 2 endpoints. When the interval is 1 to 4, from 1 to 4. So what happens when you plug in a 1 in the original function? Here it is, 5 minus 4 over x. So 5 minus 4 over 1 is going to be 1. So that y coordinate is 1, 1. What happens when you're at 4? 4 over 4 is 1. 5 minus 1 is 4. So we've got the point 1, 1 and the point 4, 4. What is the slope of that original line? That's what they're doing right here. The slope is y2 minus y1 over x2. It's 1. Okay. So now the question is, when on the function, when will the tangent line have that slope of 1? So this time, after we find our derivative, we're going to set it equal to 1 and not 0. So what's a derivative of? They never showed this, but if we take, let's take the derivative. So if we take the derivative of this, we've got 5 minus 4 over x. This is the original function. How could I rewrite that? 5 minus 4x to the negative 1 power. And then when you do the derivative, what do you get? The derivative of 5, that's 0. And the derivative of this, negative 1 times negative 4 is 4. Reduce the power by 1. You get 4 over x squared. Okay, now take that and set it equal to 1, because that was the slope of that original line. So can you solve that? Sure, just multiply both sides by x squared. You get x squared equals 4, and you get 2 answers. X equals 2, x equals negative 2. Of course, the only thing we were asked to do is find a point in the interval. So at the moment, even though negative 2 is true, we're only interested in the positive 2. So the only difference between this and the other one is, instead of setting our derivative equal to 0, now we're going to set it equal to the beginning slope In this case, the beginning slope was 1. 4, comma 4, 1, 1. We did the slope formula and got a 1. Questions? All right. So let's take a look at a problem here. Basically, that's it. Rolle's theorem, mean value theorem is the lesson. So let's go. I mean, by the way, on the assignment, you're going to see. In fact, maybe we should take a look at the assignment right now. I have completely changed this assignment. You can see, and you should probably write it down right now. It's what I wrote in black there. Number 5, number 7, the odds from 23 to 27, number 37, and the odds from 39 to 51. So a totally different assignment than what was in the exercises. Okay. So now with that in mind, let's go back to where we were. So I'm not going to look at this first section at all. So let's look at, starting with this, I think I said 5 was the first one. So we're going to take a look at number 6. In 5 through 8, find the 2 x-intercepts of the function and show that f prime is 0 at some point in between. So which theorem are we using there? Slope of 0. This is Rolle's theorem. This is the one we started off with. All right, so take number 6. Find the 2 x-intercepts. How do you find x-intercepts? How do you find where a graph crosses the x-axis? It's when it's equal to 0, right? Because it's of 0 height. So that's why I wrote this right here. Okay. When is the function equal to 0? And I'm able to solve that by factoring an x out. When will this expression equal 0? When x is 0 or when x is -6? So there are your 2 x-intercepts. All right. Now, somewhere between 0 and -6, by the way, is this a continuous function? Yeah, it's a polynomial. So there's no way that's not going to be continuous, and it's easily going to be differentiable at all. So we've got that taken care of. So therefore, we're guaranteed at some point between 0 and -6, there must be at least one other place where the tangent line is 0. So now we take the derivative of the function, and we set that equal to 0, and we find out, oh yeah, at -3, which is between 0 and -6, that's the other place. Here, let's just take a look at this. So if we do, let me get rid of that. Okay, x squared plus 6x. What was that function? X squared plus 6x. Okay, that looks correct. Oh, okay. So there we have the bigger picture. All right. What did we find as our 2 intercepts? -6 and 0, right? See, 0 and -6. All right. Now, what does Rolle's theorem say? It says somewhere between those 2, there must be at least one place where the derivative is 0. And you can all see that's down here. That tangent line would be at the bottom of that parabola, and that's what we found out right here. It's at -3. Okay, so there's the first kind of problem with Rolle's theorem. Pretty simple, I think. All right, now going a little further, and now we're on Rolle's theorem. And what we're going to look at here is some problems from the assignment. We're going to look at 25 and 26. Okay, so in exercises 23 to 28, use a graphing utility to graph the function on a closed interval. Determine whether Rolle's theorem. So the question is it legal to use Rolle's theorem here? Okay, so we're going to take a look at 25. Number 25 is right here. Obviously, I got to zoom in so we can see it better. Okay, we're just graphing that function, as you can see, between -1/4 and +1/4. That's why I had to zoom in. So there it is. It shouldn't be too surprising that it looks like that because it's related. It's got a tangent in it. Okay, and if you remember the graph of a tangent, you know it looks something like that. So the question is, if we go between -1/4 and +1/4, can we use Rolle's theorem? I'm going to put that one to you three or four. Sorry. 1, 2, 3, 4. Can we use Rolle's theorem there?
Yeah, because at 0, 0 is where. Oh, no, never mind.
Well, what are the conditions you need for Rolle's theorem? It's got to be continuous. Looks like we have no problem with that. Does it look like it's differentiable in that interval? It does. But what's the one thing missing? It's got to start and end at the same point. And because this, this never has two y points that are the same height. So the answer is we cannot use Rolle's theorem here. Okay, let's try a look at number 26 now. I think that was the other one, right? Yeah, number 26. Okay, so let's go back here. Let's undo that. Let's look at number 26. Now, that looks really strange. Looks like almost straight. But if I zoom in on this, you can at least get a view of what's going on. And we're supposed to go from -1 to 0. So you can see we start there and we end up over here at 0, 0. Does this work for Rolle's theorem? Well, it's continuous. We don't have any breaks. Is it differentiable? Yep. Is there a place? Do they start and end? Do they have 2 points that are the same height? Yep, at -1 and 0. This is going to work. This we could do Rolle's theorem on. Okay, so now what you would have to do with this is, all right, take the derivative and then set the derivative. Find out when the derivative is 0. Because Rolle's theorem works. There's guaranteed to be a point in between. So, okay, let's quick do that one. So I'm going to write this out. We've got f of x equals x over 2 minus sine pi x over 6 Okay, let's rewrite that a little bit. This is what, 1/2 x And this is the sine, and I'm going to write this like this, pi over 6 multiplied by x. Okay, what's a derivative? Well, the derivative of the first part is 1/2. What's a derivative of the sine? Cosine. Okay, do we have a chain rule there? Yeah, because, I mean, we had this inner function of pi over 6 times x, and what's the derivative of that? Pi over 6. Okay, now, when will we have a derivative of 0? And so, just set the whole thing equal to 0. You know, I could have put this pi over 6 in the beginning. Let me just rewrite this a little bit. Okay, let's write that like this. Okay, so go a little further here. See if I'm going to have space. So let's add pi over 6. So pi over 6 times cosine. Having a little trouble with my pen. So what I did is I added this thing that was being subtracted and added it to the left, to both sides, and that equals 1/2. Okay, so now let's see, if we multiply, let's get rid of this. Let's multiply both sides by the reciprocal. So that's going to be 1/2 times 6 over pi. I'm going to have to finish on the right because I'm running out of space. Okay, so that's cosine pi over 6x equals 3 over pi. Okay. Anyway, then we could go about solving that and coming down to the end. Let's see, what number is that? 26. You can look at the graph. Let's go back to the graph. You can see it looks like it happens right there. Take a look at number 26. Yeah, so like we were doing, we got down to this point. We got down to this point, and then you can solve that. You can you can solve that and find out that it's a decimal, but, and sure enough, if you look, negative 0.5756 is exactly where that horizontal tangent line would be. Okay. What else was I going to say? I'm trying to remember now. What was the assignment? Oh yeah, and you also have number you've got that stuff on the end, 37. Okay, so number 37. Let's take a look at number 37. Number 37, the mean value theorem. Consider the graph of the function f of x equals negative x squared plus 5. There's the picture there on the top of the graph. It says Find the equation of the secant line joining the 2 points -1, 4, and 2, 1. So we see these 2 points highlighted over here. And because this is tilted, this is the mean value theorem, right? So the first thing we got to do is we got to find what's the slope of these two. What's the slope from -1, 4 to 2, 1? And you'll see I did that here in part A down below. Just did the slope formula, and I came up with -1. Okay, so now they wanted us to find the equation. So now we know the slope is -1. So you can see I just did some straight line stuff, and I found that's the equation of that line. And you can see the y-intercept is 3. And if you look up here, yep, that's what happens when, that would be the point where it crosses. Okay, good. B, use the mean value theorem to determine a point C on the original function so that it's got the same slope as that one. Okay, so take the function -x squared plus 5. What's its derivative? Easy derivative, -2. When will that be equal to -1? And the answer is when x is 1/2. And if you take 1/2 and plug it in to the original function, you can find out what the y-coordinate is. Okay, that's the end of part B. Part C, what's the equation of that tangent line? All right, well, we know that the slope is -1, so that I wrote down. We also now can what? Plug in this point. Plug in y is 19/4, x is -1/2, and we can find, so we got the equation. And sure enough, if you plot them, look, do you see that here's that point, 1/2, 19/4, and do you see how we found, yep, that line is parallel, just like the mean value theorem said. Okay, so I just kind of did one of your problems, number 37, but let's just go back and look at the exercises one more time. I've completely changed them. So 5, 7, 23, 25, 27, 37, and then 39, 41, 43, 45, 47, 49, 51. That's the assignment. And I should note, I believe we don't meet tomorrow. Is that correct? Is everybody aware of the assessment day? Anybody out there? You guys know about assessment day?
Yeah, we don't have classes tomorrow.
Okay, so this is basically then for Friday. Okay. Questions? All right, thank you. I appreciate it. You have a good day. It's starting to get warmer. It's nice and sunny out there. At least it is where I am. Have a good one.